Okay, so hi everyone. I'm Saharon Rosset. I'm from Tel Aviv University. I'm a statistician. Been drifting in and out of statistical genetics over the last decade. So this is kind of my attempt at taking a step back and trying to talk about some sort of fundamental topic and then connecting it to some applications in statistical genetics. Okay, so the magical multivariate normal distribution. Okay, so as we know, a multivariate normal, we're going to denote it. We could just say it's normal, but to emphasize the fact that we're looking at a vector, we'll call it MVN, multivariate normal. And it has these parameters, the mean vector and the covariance matrix. And we can write down explicitly what the density of a multivariate normal is. I don't know, to some people it can look like a very nice formula. To some people it might look scary, but it's a very fundamental, very important kind of formula that we're going to come back to. Okay, and the point is that once if we work hard and integrate these things, we're going to find out that indeed if a multivariate distribution has this density, then its mean vector is mu, and its covariance matrix is going to be sigma, right? So these parameters have a meaning. And we can think of it, we're going to think of it in 1,000 or 10,000 or 1,000,000 dimensions, but we can draw it in 2 dimensions, and this is what a bivariate normal looks like. What's the covariance matrix of this? The fact that we have this nice symmetric structure. What does it tell us about the covariance matrix? It tells us that the covariance matrix is orthogonal. For example, it might just be unity, right? Identity covariance. And we can also see the means by looking at the centers of this. It's a bit too small, the font, but the means would be these projections on the axis, the mean vector. Okay. So what makes the normal distribution magical? Many things make it magical. I'm going to focus on a couple of them and then maybe mention others when we move later. One very important magical property is the fact that it's a closed family. So one thing we hopefully all know already is that the normal family of distributions is closed under linear transformations, meaning I take something that's normally, so I'm sure we all heard in Stats 101, or we should have heard that if we have a univariate normal random variable and we do a linear transformation of it, then it's still normally distributed. It might seem trivial, but it's actually, well, it's not the only distribution that has this property, but it's really a unique property, the fact that I can do transformations, linear at least, and remain in the same family of distributions. And the same thing basically holds for a multivariate normal. So I take some multivariate normal vector, I do a linear transformation of it, so A is a matrix, right? And the number of columns of matrix A is the dimension of X. The number of rows of A might be different, so I might be changing the dimension after I apply the transformation. That's fine. So A is some matrix with n columns, because we said X is of dimension n. And B is a vector that has the same number of entries as the row dimension of A. And after I did this linear transformation, I have, once again, a multivariate normal distribution. Now it's going to be, say that M has Q rows and, as we said, n columns. Now I'm going to have a multivariate normal in RQ instead of Rn after I do the transformation, but it's still going to be multivariate normal. So this is kind of a Stats 101 property. A second property, which is maybe less trivial but probably more important, is the idea of conditioning. So the really cool thing is that once I have a vector of random variables and I condition on some of the coordinates, on the value of some of the coordinates, the conditional distribution of the other coordinates remains normal. Okay, so let's go through this. So now, before I just had the vector x, now let's divide this vector in two parts. One I'm going to call x, and the other I'm going to call y. Both of them are vectors of any dimension I want. Okay, so neither of them is a scalar, and they don't have to be of the same dimension. And now I think of them as having of the vector where I concatenate x and y now has a multivariate normal distribution. So this is something I'm assuming, that I start from a multivariate normal vector with this vector of means, which is a concatenation of the means, and this covariance matrix, which is the covariance matrix of x, the covariance matrix of y, and the cross-covariance matrix of x and y and its transpose, right? So, and now I condition, so I observe y. What does conditioning mean? Conditioning is this very scary probabilistic context, but what it really means is that I get to observe y, and I want to see what I've learned about x, right? And now this is not an abstract context. This is something that basically everything we do in statistical analysis, we can think of it in that context. We're interested in a bunch of things. We're interested in something that's unobserved or we want to predict. We get to observe some other things, and we're interested in the conditional distribution or learning something about the unobserved elements from the observed elements, right? So this is really a question about conditional distributions. And the important thing is I get to observe y, what have I learned about x? So x, given that I observed y, x still has a multivariate normal distribution. Now it has a mean that is like its own mean, and it's shifted. How is it shifted? I take the difference of y from its mean, and I multiply it by these elements from the covariance matrix. And what does that do to the mean of x? What does it do to the mean of x? For example, if y is much bigger than its mean, what's going to happen to the conditional mean of x? Is it going to be bigger than the mean of x or smaller than the mean of x? There's actually no one answer to this, right? It actually depends on the nature of the covariance matrix. But in the typical case that x and y are positively correlated, so basically they tend to be similar to each other, which is what we have in many cases, then if y is bigger than its mean, this expression is going to be positive, and we're going to see the mean of x pushed up by observing y. Okay, so the mean is going to be shifted by what we've learned from observing y. What's going to happen to the covariance matrix? We have here this expression for the covariance matrix of the conditional distribution. So this is just the x part. We moved from having sigma xx to having this expression. What can we say about this expression compared to sigma xx? Is it always going to be smaller, the variance, once we observe y? Is it always going to be no bigger? So let's think logically about it. I'm interested in knowing something about x, and I get to observe some information that's not exactly x, but is somehow related to x through this joint distribution. What should happen to the variance, to my uncertainty about x? It should decrease, right? And we can algebraically convince ourselves that this is decreased, but really that argument that observing something always has to not hurt our information, it can only improve it, tells us that it has to be the case that this covariance is smaller than the covariance we started from. So this also makes sense, because everything we do is we observe something, and we want to learn about something else we didn't observe, and we have learned maybe nothing, but no worse than nothing by observing the partial information, right? So that's captured by the fact that the covariance, so say the determinant of the covariance has not increased, or if this is just a scalar, then the covariance has decreased if x is a scalar. This is also an expression of those of you who heard my talk last year know that I love the law of total variation, so we can think about this also as another expression of the law of total variation, meaning the variance of a random variable is the expected value of its conditional variance, conditioned on something else, plus the variance of the conditional expectation. So this is the conditional variance. Since the conditional variance is fixed, then its value has to be smaller than the marginal variance we started from. So this might not be the best ever illustration of the law of total variation, but I still think many things we do are made clearer by thinking about them in the context of law of total variation. Okay, so this is just an illustration of this idea. So I start from a standard normal, which is this dashed distribution. Actually, what I have here is 3 different cases of the distribution of x. So x and y are just bivariate. I have, each of them is a univariate, so x and y together have a bivariate normal distribution. I condition on y equal 2. Okay, so, and I look at what happens to the margin, to the conditional distribution of x given y equal 2. So we start from the case of no correlation between x and y. If x and y have no correlation, what's the conditional distribution of x given y equal 2? It's just the marginal distribution of x, which is a standard normal in this case, right? So this is the dashed line. Because I've learned nothing, if they're uncorrelated, I've learned nothing from observing y. Okay? What happens if they have negative correlation? Then if they have negative correlation, learning that y is positive actually pushes the distribution of x towards the negative side. And the fact that this green is slightly higher than the dashed means I've learned something, right? My variance is smaller now. My distribution is more concentrated. So this is a small negative correlation. If I have a big positive correlation, I've learned a lot. And I also learned that x is most likely positive because y equal 2, right? So we can think of sort of the importance of the conditioning and what we've learned from the conditioning. Okay, so this is nice. Now we're going to train in using what we've learned to learn something that may not be as intuitive. So really what we do many times and what we're going to be doing next when we talk about linear mixed models is we can think about what we do is taking a high dimensional normal random vector and say that these are all normal standards, so the standard normal, so they have mean 0 and variance 1. We don't worry about the marginal variance or the marginal mean. This is the simplest case, but it's a correlated vector. It's a vector of correlated normal random variables. Okay, and now we have a correlated vector of length 100,000, and we sample one vector from this. Sampling one vector from this is getting 100,000 observations. That's a whole lot of data, but it's just one sample from this joint normal distribution. And the question that we might be interested in is what does the empirical distribution of this vector look like? So, and the 2 options we might consider are, we've sampled 100,000, we've learned all kinds of things like the central limit theorem and so on. So do we expect that at 100,000 the correlations will basically cancel out and what we get will always look like a sample from a standard normal? Or is it possible that we'll get something, even though we have 100,000 measurements, that looks completely different from a standard normal? Okay, so this is important because I think, for example, in LMM, many people are taking the data and asking themselves, does this data look normal? And if it doesn't look normal, then maybe the LMM doesn't fit. So if the second answer is correct, then that's not a good way of testing whether a bunch of data came from a multivariate normal or not. Okay, so let's try some quizzes on this. So in each one of these plots, I have in dashed the standard normal distribution, and in red, a suggested sample, the empirical distribution of a suggested sample. This is not in 100,000 dimensions, it's in 1,000, so it's not that much data, but a suggested sample. So can my sample have this empirical distribution, which is basically a noisy version of the standard normal? Of course it can, because it might actually be a sample from an IID standard normal if my covariance matrix is just the identity matrix, right? So this is easy to answer that this can easily be a sample. This can, the sample from the jointly multivariate normal might well look just like a sample from a standard normal distribution. Now it's getting more interesting. Can the empirical distribution of my random normal vector, can it actually look like this, very concentrated and completely different from the standard normal? So I see heads nodding. I see some negative answers. So The answer is that it absolutely can, and this is actually a sample I drew from a jointly normal vector. And what kind of vector would have this distribution? So a vector where I take all the off-diagonal elements of the matrix, of the covariance matrix, to be very big. So basically, I have a very highly correlated sample. And what have we learned previously? That the conditional distribution of highly correlated random variables, the condition of one on the other, is very concentrated, right? So I can think of this joint, of this sample, as maybe I just drew the first one from a marginal normal, standard normal. Now everybody else is very highly correlated with this one. So everybody else has a distribution that's concentrated around the one I drew. Now the fact that this is centered at around 1 and not at 0 or -1 is completely random, right? It's like the first draw we did. By symmetry, it doesn't matter who we drew first, but I draw a random sample again. I might have a Gaussian that's concentrated. I might have this peak concentrated at -2 or at 2. So the point being that this is actually a random sample from a jointly Gaussian vector with marginal distribution standard normal. Okay, so let's make it more challenging. Can this be a sample from a multivariate normal distribution? Okay, so hopefully we all understand that once, so maybe one thing we understand is that the answers are yes to all my questions. So the answer is yes to this one as well. And why is the answer yes to this one? Because now, instead of having everybody being highly correlated, we can have a bunch of positively correlated and a bunch. So basically, we can think of this as a two-population model, right? And again, the fact that these guys are at minus and these guys are at plus, I don't associate. So one peak is associated with these guys and one peak is associated with these guys, right? But it might be the other way around the next time I draw the random sample. And it might be that the peaks get closer, although if I make these correlations negative enough, it's unlikely that the peaks will get closer. So from a two-population model, so this thing that's not only not normal looking, it's even not unimodal, it's still a random sample from a multivariate normal distribution. Okay? So we're going to be talking about inverse normal transformation for LMMs. We can already convince ourselves that that's a very bad idea, given that this might actually be a sample from the distribution we're assuming on our data. Finally, can a sample look like this? So what I tried to illustrate here, and I had to do some tricks for it, I tried to illustrate a non-continuous distribution. Okay, this might look familiar to people who do a lot of GWAS, but the point is that I have a non-continuous distribution. Can my empirical distribution be, well, an empirical distribution is always non-continuous, but doesn't give the impression of coming from some continuous underlying distribution. Is that something that makes sense in the context of sampling from a multivariate normal? Okay, so that was a trick question because the answer now is no. Because whatever the covariance, the conditional distributions are always continuous, and the empirical distributions should always basically look continuous. I mean, this kind of behavior is something that's, you cannot generate this behavior by doing a sample from a multivariate normal. How can you do this? You can do this by drawing a sample from a simple normal and then upweighing the points that are big, right? And this emulates what happens in case control sampling in, say, the liability threshold model that I'm going to be talking about. So this is one thing that does not behave like a multivariate normal at all when you see this kind of non-continuous behavior in the sample. Okay. So what we've learned so far, we've talked about the fact that the conditional distribution is still normal. and it has smaller variance due to the law of total variation or the learning by getting information or whatever abstract concept you want. And the mean is attracted by the observed data, or it might be repelled if there's negative correlation. And we've learned that the samples drawn from this, it's a single sample, but it's 100,000 observations, so it's basically all the data we're likely to have. But it's sample from this correlated world where things are not independent but correlated. We've learned that it can have a variety of forms, and the typical form of the sample depends on the covariance structure of our data. Okay? And the most important lesson is even large samples. Large samples meaning a single sample from a high-dimensional Gaussian, from a high-dimensional normal. Not many independent samples from, so if I have a 1,000-dimensional normal and then I draw 100 samples from it, and I look at the empirical distribution of the 100,000 samples that I got, that's typically now starting to look like a standard normal. Why? Because I have this peak, but the peak is moving between my different samples, and when I draw many different samples, it's going to integrate out. And I know it's going to integrate out correctly because I know the marginal distribution of my data. But for a single sample, which is a long vector, we should not expect this random vector to look to have a normal empirical distribution. Okay, so this brings us to thinking about linear mixed models, and what we're going to be doing in linear mixed models is basically trying to take our thinking about normal distributions and expanding them to predictive modeling, to modeling some dependent variable. And one thing I want to emphasize for this audience is that the linear mixed model, first of all, as we're going to see, it's basically using the normal distribution in several different ways. And it's been popular for decades, for at least 50 years in many different fields, including in genetics and biostatistics, long before it was ever applied, long before there was ever GWAS or it was applied to GWAS. And it's very popular in areas like spatial statistics, in ecology and brain studies, in longitudinal studies, which are also common in biostatistics, and family studies, which are also common in biostatistics, but in other fields as well. And what's the general LMM model? The general LMM model is basically, some people try to talk about LMMs maybe in Bayesian terms, but it's kind of the most non-Bayesian thing you can think of when you think about an LMM. Why? So what we have in a regular, say, linear regression is we have some observed vector, which is of length n, and this observed vector is the result, or we assume, we may assume that it's the result of doing some linear transformation on a bunch of features, which are rows of this X matrix, and the linear transformation is captured by this vector beta of coefficients, and then adding noise to it. When we think of an LMM, we add another element to this. So the fixed effects is what we have in a regular linear regression. When we think about an LMM, we add something we call random effects, which in these representations look exactly the same as the fixed effects. But a fundamental difference is that this vector of beta is a vector of parameters. So these are fixed and unknown values that we want to estimate. Whereas this vector b is a vector of random variables that are not parameters that we want to estimate. They are sort of a characterization of our model, the fact that we think that this vector b exists and is random and has a multivariate normal distribution. Here I assume it has an identity or scaled identity covariance, but that's actually not necessary. We can assume different covariance structures on b. And then we have this vector epsilon, which is a multivariate normal as before. Okay, so without this, we would have a standard regression model, assuming normality. So that's something we may or may not want to do in a standard linear regression, but we have a version of standard linear regression. Once we add the random effects, it's no longer a standard linear regression. The most important thing that happens is that now the elements of y are correlated. Why are the elements of y now correlated? Because we have this z times b. So the coordinates of b might be independent, but after we mix them with the z, that means that the rows of y we get are now not independent anymore, right? So we get the representation, which many of you may know. We can think of this vector y. It has a multivariate normal distribution because x and z are fixed matrices. So this is just a constant that's actually the mean of the multivariate normal. The fixed effects are the mean of the multivariate normal. And the random effects plus the random noise, they give us the covariance matrix of our multivariate normal. Okay, so this is what an LMM would look like. So the example that's probably of most interest to us is LMM modeling of GWAS. So what would X contain? X is the fixed effects. X would typically contain things like sex, age, gender, maybe population affiliation. We'll talk about that a bit later. And we might want to include special SNPs that we think are very important in our fixed effects because we want to estimate their effect. We want to estimate their beta. Okay? What would the matrix of random effects, what would it contain? Typically, it would be the genotype matrix. So I denote by P the number of fixed effects I have, and in what follows, I'm basically, for simplicity, going to assume that I have no fixed effects, although there's nothing complicated particularly about having them. But I can have a lot of random effects, and in GWAS, I make my genotype matrix the matrix of random effects, so I might have something like 1 million random effects. And why do I have to make them random effects? So there's different arguments in genetics, but the general spirit of it is I have so many, I have no chance of estimating 1 million parameters with any sample I might get. But if I treat them as random variables, I don't have to estimate the parameters, right? How many parameters does this representation have? So I think I have it here. This representation, if p equals 0, this is actually an empty vector. All it has is 2 parameters. That's the variance of the random effect and the variance of the random noise. So instead of estimating 1 million parameters, I estimate 2 parameters, right? At the cost of assuming my model is correct, of course. So now I want to estimate my parameters, and the standard way of estimating them is doing a maximum likelihood for beta, but my beta is empty, so I don't have to do it, and doing REML for the variance components. But if I don't have fixed effects, then basically doing REML is doing maximum likelihood, so I can just think of it as doing maximum likelihood. I have to write the likelihood function and maximize it with regard to these variance component parameters. And when I've done all this, one thing I'm often interested in GWAS, especially if I have no fixed effects and special SNPs, that might be all I'm interested in, is this notion of heritability, which is, we can think of it as the percent of the variance of y that's explained by the SNPs. And in my notation, it's going to be the number of SNPs times the variance of b per SNP divided by this plus the environmental noise. In genetics papers, you usually divide the matrix ZZ transpose by Q, and so here you would not have that factor Q. But this is basically my reformulation of the standard SNP heritability estimate in LMM. Okay, so one thing we might want to ask ourselves, these assumptions we made, there's actually a lot of assumptions here in this model. The assumption of linearity of effects, and the assumption of normality of B, normality of epsilon, the independence of the non-genetic effects of the non-random effect. There's a lot of assumptions here. And so we might want to ask ourselves whether the assumptions make sense. And one that we might be particularly worried about, I think the one we should most be worried about is linearity in general, but the one we're often worried about is normality. So does it make sense to assume that things are normal? So one thing we might tell ourselves, and I think with good reason, is that because Q is very big, we have the central limit theorem helping us, right? So actually, we don't really have to assume that the elements of B are normal. They might have any distribution we want, as long as they are IID or not even IID, but some nice behavior. And the central limit theorem is going to tell us that this element, this object Z times B, is still going to be very close to normal. So I think that being concerned about normality of the genetic effects is not a major concern. One thing we may be very concerned about is whether the epsilon element, where we draw the environment, what we call environmental component for each observation, does it make sense to assume that this is normal, and does it make sense to assume that they are independent between them? So these are things we do have to worry about. And one thing we may ask ourselves is, can we look at our data in some simple way and say whether or not this data, these observed phenotypes, are likely to have come from this LMM that we posit? And so one common practice is to look at the distribution of Y. We can look at it marginally if we're very naive, or we might condition on X's and say, okay, the X's say that the mean of each Y is in a different place, but once we take them out, it's going to look nice and normal. Okay? So given what we showed before, that this approach makes sense. So it does not make sense, because we do not expect a random sample from a correlated vector of Gaussians to look like the marginal distribution. And one thing that we really don't want to do is this thing called inverse normal transformation, which is saying our data doesn't look normal, so let's force it to look normal by doing some transformation, some monotone transformation that makes the empirical distribution appear normal. So let's just see why this is a bad idea. So let's take a sample. So what the inverse normal transformation does is this. We have a sample from LMM. Let's assume it's already sorted, so it's from the smallest to the biggest. So doing an INT is basically just applying the inverse cumulative normal distribution to the order statistic of our data. And what it does is we have some distribution that looks like this. It's going to make it look exactly like it was a standard normal, right? And the point that we made before is that this red one might actually be a real sample from a correlated Gaussian. And if we made it look like this, we've lost the structure, the covariance structure that actually governed our data. We've eliminated it. Okay? And one very nice result from the master's thesis of my student Gal Naamani is that under some simplified assumption of having a fixed correlation within each population and then having them very well separated, you can do a calculation that's saying after we do this inverse normal transformation, we're actually going to get deterministic heritability. No matter what the heritability was before, it's always going to be the same after we do the inverse normal transformation, this 2 over pi times rho. And you have to assume that rho is very big, because otherwise it's close to 1, because otherwise you won't get this very distinct structure for which this calculation holds. So it's not an important result, just cute that you can see that under some extreme assumptions, after you do the INT, heritability actually doesn't depend what it was before, it's fixed. Okay, so I'm not running very well on time, but this is really what I wanted to get to. So key question we always ask, and was already mentioned here today, about LMM is about population structure or other structure encoded. And where is this structure? It's in the genotype matrix, right? And so what does it mean to have structure when we think about it in terms of the genotype matrix? So one extreme is we might say that the rows of this, so the samples, the genotypes, are drawn independently for each individual, independently of each other. And in genetics, we call it a homogeneous population, but it's really a homogeneous population only under normalizations we are used to in GWAS, like standardizing the columns. So yeah, I'm not going to go into it, but this is really just saying that there's no dependence in the way Z was drawn, in the way the genotype matrix was drawn. So we can think of it in the context of genetics as having no population structure whatsoever in our data. The other extreme might be that we have clusters of identical rows in Z. So having clusters of identical rows in Z is like having, say, not just twins, but monozygotic tuples, bunches of our data which are actually exactly identical genetically, right? So this would be the other extreme. And the question we might ask ourselves, which of these settings or intermediate settings are actually more favorable for estimating variable components and heritability in linear mixed model? And the answer we often get in genetics is that this is what we want to estimate heritability. And this answer is correct only given this concern. The concern that if we have stratification, if we have some structure in our data, it might also be associated with the non-genetics. So people who are from different populations, they eat different things, they live in different places, and so on. If that is our concern, then it's true that we want a homogeneous population. But actually, if we want to estimate heritability well, and we can think that the stratification is not related to epsilon, so the elements of epsilon are independent of the stratification, then actually we would do much better in a stratified population compared to a non-stratified. 3 minutes? Okay. Okay, so I have no time to go in details. I'll just say that so really what we care about is, as was already mentioned, we care about the spectral decomposition of Z, the eigenvalues of ZZ transpose. And in the absence of structure, we know a lot about what this looks like from the Marchenko-Pastur law. For example, that the eigenvalues tend to concentrate. On the other hand, when we have significant stratification, we can have very big eigenvalues. And in particular, if we have these two population structure, we might have a top eigenvalue that's of order square root of the size of the population. And this has major implications. So I'll go very quickly, and this is a paper by Andy, who's sitting here, and a couple of others, so you can talk to Andy about it. What they show is that in the homogeneous population regime, so we can think of our error in estimating heritability as a combination of a bias component and a variance component. And what they show is that in the absence of population structure, there's basically no bias, but the variance can be very big. And I don't have time to go into it, but we can really understand the reasons for it. On the other hand, in the presence of structure, we can have more significant bias, but the variance may decrease very significantly. And since variance is dominating our heritability estimation error, it's likely that in general, in populations with structure, we would do much better in estimating heritability than populations with no structure. So this is the take-home message that I want us to take from this part. I'll say just one word about this, the same student, Gal Naamani. So the results in Andy's paper are symptotic. Assuming some very simple population structure, he was able to explicitly derive the expected value of the heritability estimate and show the way that it's biased when the population is very structured. So it has this very interesting structure with bias, which may be significant. Okay, conclusions about LMM. That structure and stratifications in general are your friends when estimating heritability and would give you more accurate heritability estimates, unless it's correlated with the environment which violates your model, in which case you should account for that. Inverse normal transformation is most definitely not your friend in analyzing this kind of data. Okay, I have to skip over the rest. I just need to mention this. Liability threshold model and GLMM, those who don't know what it is will have to bear with me a second. Elazar and Eran asked to give reference to work that started at CGSI. So this paper, which just appeared in the American Journal of Human Genetics by Omer Weisbrod. Why is it not projecting? Okay, so It's not projecting, that means. So this paper, which just appeared in the American Journal of Human Genetics, is actually a result of work that started 2 years ago here at CGSI with my student Omer Weisbrod and Jonathan Flint. And I highly recommend it, although I don't have time to talk about it. All those who want to become millionaires will have to look at my presentation online using the multivariate normal distribution. Okay, to summarize. Trying to be cool, probably unsuccessfully, I would say that it's like really useful, the multivariate normal distribution. And we haven't talked much about the central limit theorem, but the central limit theorem tells us that many things, it's not a major assumption to assume that they are normally distributed. The closedness under conditioning is a very important statistical property. I haven't talked at all about computational properties, but they might even be more important. The fact that we can do high-dimensional integrals on conditional distributions, it's really, for example, all Bayesian statisticians do is these integrals, and for normals they can do them, and for basically nothing else. So it's pretty much the only distribution we can work with when we work in high dimension. And there's many applications beyond what we have discussed, and Gaussian processes are a natural and simple extension of LMM. Expectation propagation is actually more on the computational side. When we want to calculate integrals of complicated non-Gaussian distributions, we basically approximate them with with normal distributions and other things. And I was asked to leave the slide of the location of the posters at the end of my talk.